very pleased we are very pleased to have Lisa Michel, who will be starting and give us an overview about this transversal project, SpinMat. We'll have Jean-Louis Guyot from Ribert, Christine Walsh from Vinci Technology, Jérémy Sylvain from Tescan, and Stefano Bonetti from RARA Factory. So I'll just give the floor right away to Lisa. And I think we can just, is that it?
Thank you. So it's, thank you for the introduction. It's my pleasure to present you the transverse project of SpinMat on advanced spintronic material. So this project is coordinated by Vincent Cros, and there are 5 work packages or pillars that I'm going to present you, respectively led by Michel N, Nathalie Villard, Johan Corot, Pierre Senior, and myself. So the objective of SpinMat are threefold. First, it aims at creating a transdisciplinary material platform for the development, optimization, and scaling up of the next generation of sustainable spintronic material. And for that, the first milestone was to increase the production capability of SpinMat by the acquisition of new equipment or the upgrade of some other. And here you can see some example of equipment that were recently installed in some of the labs. The second objective is to propose new material opportunity to the spintronics community, including the other moonshot and open call project, but also to the other transverse project, for example, to test new characterization tool or new theory. At last, it aims at building the spintronics material community to foster the development of new solutions, train youngsters, and sustain a material culture. And so to sum up, SpinMat is a dedicated platform of material to serving the spintronic community in the limit of the state-of-the-art growth condition or not. So to meet this objective, SpinMat is structured around 5 pillars that represent different type of material and TRL levels, ranging from state-of-the-art to emerging approach. 22 laboratories participate to SpinMat, and we hope by the end of the project there will be more labs involved. So now I'm going to briefly present you the 5 pillars, the 5 work package, and starting by the first one, which is the most advanced in the TRL scale. That is the material and heterostructure for functional spintronics. And by functional spintronics, one have in mind efficient oscillator, efficient sensor, advanced logic device, with the aim to develop process on tools with the industrial standard. And there are many examples, and here is one recent example of an optimized magnetic heterostructure leading to ultra-fast or picosecond and energy-efficient spin-orbit torque switching, which opens the route to a functional spintronic device with very high speed. And that involves material engineering that require a precise control over thickness, interfaces, and composition. The second work package focuses on oxide, taking advantage of their versatility and the multiple functionalities. And it aims at the production of garnet, thin film, and other material for low damping, at the realization of heterostructure for beyond CMOS technology and also for terahertz technology. And also, it's got in mind the integration of the oxide heterostructure onto silicon. So here, it's a recent example of the synthesis of freestanding metal oxide nanocomposite membrane made of vertically aligned cobalt-nickel nanowires within a STO matrix. So the unusual strain state and therefore the magnetic property of this wire, the nanowire, are kept intact through the through the removal from the substrate and the transfer to another substrate, which opens the route to, towards substrate-independent implementation of oxide-based nanocomposites. The third work package focuses on 2D magnetic material with well-controlled properties. The objective are the production, the fabrication of on-demand individual magnetic 2D with large 2D material with large surface, their integration into advanced heterostructure, and also the investigation of the emerging functionalities in this heterostructure. As an example, here are a study of van der Waals ferromagnet in which the chiral structure was stabilized via DMI, and that is combined to low magnetic dissipation, which make this system highly promising for the study of dynamics in chiral texture in 2D material. The fourth work package addresses molecular spintronics. So it takes advantage of the potential of chemical engineering and wants to bring it to spintronics. The first aim is, of course, to synthesize the molecule, then to characterize them when they are grafted to a ferromagnetic substrate or layer. And then it aims at fabricate devices and evaluate their potential. Here, in this study, this study is about the large area molecular junction based on helical complex. This constitutes a stable and durable platform for spin transport through self-assembled monolayer. The last work package takes advantage of proximity effect and competitive interactions that can emerge from heterostructure in which you've got layer that got a very radically different spin order. For example, topological insulator with superconductor or with antiferromagnet. And in this work package, we aim at the production of heterostructure for spin charge conversion, spin polarized superconductivity, or for spin texture manipulation. As an example, here's a generation of a 2D electron gas at the interface between STO and a layer of nickelate. And the conductivity can be tuned by 5 orders of magnitude via an optical stimulus, which open the way for optical monitoring of the superconducting nickelate. So from all these examples, you see that a lot of challenges that need to be addressed. And so high-quality interface, heterostructure, integration of different synthesis strategy, and that is particularly true when you there is the growth of different kind of type of material, large area bottom-up growth TRL, compatibility with CMOS technology, and that is combined with on-demand property. So to answer this demand, we need first for adequate substrate, and to illustrate that, for example, STO, it's the ideal substrate to grow most of the oxide, but it poses limits for terahertz characterization due to high absorption. And Matec, for example, developed a solution that's silicon substrate with an epilayer of 4 nanometer of STO for subsequent growth. And also, but that is something that is, there is a solution, but for other cases, it's difficult to find certain substrates, such as GIP 111, germanium 111, good NGO 111, and so on. We also need for high throughput growth material for combinatorial study, alloy property optimization, to get a gradient of thickness with sub-nanometers resolution, to also study the impact of the microstructure. And that is an example, for example, here, where you can see that the study of the effect of cobalt thickness on the magnetic property within a simple, a single stack with a cobalt, well-mastered cobalt wedge. And this study shows also that we need some high throughput characterization, for example, to evaluate local thickness, magnetic property, but also topographic, crystallographic phases, resistivity, composition, and so on. And the last example shows this screening of hard magnets through a high throughput approach, combining so high throughput growth, and also fabrication, characterization, and analysis. So just to conclude, that's the main message of my presentation. And so to address all this challenge, SpinMat is open to establish and strengthen the collaboration with all of you, and either to develop or test material-focused strategies that can be for changing the property, for new substrate, tools, and so on. I thank you for your attention.
So thank you very much, Lisa. So we decided that for this session, we would keep all the questions at the end. So I will ask Jean-Louis Guyot to come for Ribert. And I think, so the floor is yours. And c'est ça.
My name is Jean-Louis Guyot, and I'm coming from Ribert company, 100 people. Okay, we start in the 80s. We are born with the 3.5 semiconductors, where we develop a series of systems with increasing the size of the wafer from the first Rebirth 32 machine, and at the end, the supra chamber, which is a chamber which is able to grow supraconducting films at 100K, okay, over a 4-inch wafer. And also in the 90s, we start making mass production, which is in Europe, there is no mass production machine. Okay, this is mainly in the US and in China now. Our workhorse is the NB6000, okay, used for 3.5 semiconductor, arsenic phosphide, antimonites, nitride, and nitride. Because this is a machine producing four times 6-inch wafer, And in 2020, we made the biggest machine, the MB8000, being able to handle the 4x 200 millimeter, because Calais-Marsonnay is coming on 200 millimeter. I will not discuss this, okay? Thus, I will tell you what we are doing now. Okay, we have the smallest machines, MB machine. We have the largest MB machine, okay? And what to do next? Next is entering into silicon, okay? Our core business is making epitaxy. Epitaxy is all the marvelous device you say now is the combination of new materials and interface, okay? MBE is mandatory and known to have the possibility to manage properly the interface. And we have developed the ROSI machine. ROSI machine is a 300 millimeter machine, okay? And is compatible with the silicon industry. Thus, this machine can handle a full cassette of, let's say, 25 wafers in a run. At least, this is the promise of that prototype. Okay, that's why Ribert goes into the silicon industry with this new kind of material, which is the barium titanium oxide. Okay, because barium titanium oxide has a unique feature. This is a ferroelectric material. Okay, and one of the properties, because there are many properties for this material, pyroelectricity, piezoelectricity, one of the target we are focusing right now, okay, is the use of this huge Pockle effect, meaning that with a small voltage you are able to change the index of refraction. There is many applications behind that. This is, of course, the high-speed datacom, because with such a material, you have the promise to reach high-speed electro-optical modulation for datacom telecom. Of course, there is also the computing, okay? Optical computing, not quantum computing. There is also the sensing, like a company from Leti, or spin-off from Leti, who make LIDAR and a steering light with only voltage, let's say. This is made with electro-optical modulator. Right now with silicon, thus with a high level of losses. However, with this barium titanium oxide, the promise is to have low loss. And quantum computing. The emerging of the barium titanium oxide into production, okay, is coming from the quantum computing. There is one company in the world which is called PsiQuantum. PsiQuantum make its pillar. The company is built on 3 pillars. The first pillar is a perfect electro-optical modulator with low loss based on barium titanium oxide. The second pillar is cryogenic, management of the cryogenic, and the third is the computing. Okay, and they already have $6 billion leverage of money. Okay, to do that. Thus, we enter into that game by making this new machine. However, you should understand that Ribert has started with 3.5 semiconductors. 3.5 semiconductor was really young, okay? Thus, the business of the 3.5 was to say, I think about a structure, I make the structure, you make the structure, and after you make a device based on that structure. This structure is a stack of different kind of material, and the interface, perfect interface, makes the properties you want to see. With the same machine, you are able to make transistor, you are able to make RF amplifier, you are able to make lasers, you are able to make, let's say, detectors, okay? Changing the material, arsenic, phosphide, and so on. You can cover the range, or nitride, you can cover the range from blue to far infrared, okay? Sorry, far infrared, okay? With the silicon world, it's not at all the same. I will not give a machine saying that this machine is a 300 millimeter machine, okay? If you put 10 PhD, within 3 years or 4 years, maybe you will find a recipe. I need to develop the recipe by myself, okay? Put the recipe into the machine. The IP for a system maker is the way to warm up a substrate without breakage. The IP for a system maker is to guarantee that I have 85% of throughput and so on. Thus, we have here, this is our roadmap. Thus, we first develop a first prototype machine. This first prototype machine has been hooked up in NQCP NBI, Niels Bohr Institute. Okay, NQCP is the foundation for quantum computing. Okay, and with this machine, which will be handled by RARA, okay, we will be able to produce some few samples out of the main program, which is POEM. Okay, and our second project is ROSY 2. ROSY 2 is a dual reactor machine. Okay, also 300 millimeter, probably downscale to 200 to address more standard fab and so on. Okay, but which will be able to produce 1,000 to 2,000 wafers a year. Okay, why I do that? I'm a system maker. I'm not let's say a wafer maker. Okay, but if I want to learn how to make a production machine working, okay, for industry to move fast from your idea to mass production, I need to work on production, to make production. Who is going to buy this machine? Here, no one. Okay, thus I need me to invest into that machine, to let this machine work with you in the community, just to make your project close the bridge between TRL 3 and TRL 5. Okay, thus this is our roadmap. Thus the ROSY 1, which is the prototype machine, is operational right now. We are starting producing our first wafer, just to see, of course, the uniformity, and also to start growing the STO on silicon. Thus, STO on silicon is one of the key. For example, if you have to address or to bridge between R&D to fab like LAT and so on, okay? And the second, PHB, which will be hooked up in Q1 2027, okay? Thus, this is the productivity of the machine. Thus, the machine here is dedicated really for making industrial sampling or R&D sampling. It means that this machine will not produce only one kind of materials. Based on research environment or ecosystem, we will be able to work with you, with other in the photonics and so on, just to elaborate new material, new stock and so on, and to let this machine. Why I put this machine? Because to learn how to produce, we need to produce. Okay. But no one now is able to buy 1,000 wafers. No need. LAT, for example, they want first 5 samples. This is chicken and egg. You know the story of the chicken and egg. Everyone want to have omelette. Okay, no one won't buy the chicken because they don't know if the eggs are good or not. Thus, this is exactly the story we are. Thus, I put this machine by my own somewhere. Okay, so has that this machine can use. Thus, let's come back to POEM. POEM, this is a collaboration program between RARA and NQCP, dedicated for developing optical modulator for quantum computing, okay, with NBI, photonic oxide engineered material. Thus, the scope of work for RARA is to develop the epitaxy of barium titanium oxide STO on silicon, okay, for the quantum computing, which is the toppest level of the material quality. This is for quantum computing. You have only one single photon, thus if you lose some of them, it's a drama, okay? Of course, our target is to put into that machine some recipe, so as that it's good enough to address other markets like datacom and telecom. Okay, and NQCP, of course, is integrate those novel material and build the optical, the quantum computer. Okay. However, this machines is in Denmark into POEM. Thus, all the material will be used by POEM. We will be able to have some sample, okay, to deliver to the community, just for them to make omelets and see if the omelets are good and so on. Thus, if they can proceed further by or putting new R&D program and so on. But this will be limited because this machine is hooked up in a, let's say, an academic environment. Okay. Thus here, let's come on see the team. Thus, in Denmark, we have 2 PhD working on the machine to develop the process and so on. We are surrounded, of course, with the, all the academics and so on for the measurements and the measurement. Thus, the end of hookup has been done in March 2026, and in September 2026, we will have our first STO on silicon and BTO STO on silicon. Okay. Thus, the guy here with our first substrate, this is titanium directly on silicon, is Nasser. And here we see Maggie, okay, which have a wafer, 300 millimeter wafer with titanium oxide on silicon. This is only for demonstration of the uniformity. Thus, we are over 300 millimeter, less than 1% uniformity. Okay. Thus, this team is making research to develop recipe compatible with a production machine. Thus, let's see the phase 2. Phase 2 is Phoebe. Okay, that this is a more productive machine. Okay, more productive machine or more flexible machine. We understand that barium and strontium is maybe not enough for some of your project. Maybe some of the project needs to have ruthenium, have other kind of material and so on. Thus, however, this machine needs to let's say, this is a machine which address all the people, the photonic industry, d'accord, or the photonic actors for the barium titanium for the development of the electro-optical modulator, but also all the people who use functional oxide for other function, like electronics and so on. That's one good example is this spin-off of Leti and Thales with Nello. Okay? Does no, yes, sorry, close by. Okay, thus this is our production tools, okay, which can be, one will be configured purely for STU, BTO, okay, because this is, okay, yes, I'm speaking too much. Okay, but the idea here is to evangelize the EU with this new material. This material seems promising, but no one can buy it, or piece of them, or okay, thus we need to build a standard. Thus functional oxide, with Phoebe, you will be able to have functional oxide AP wafer to work with us to develop your own stacks or your have your advice for the property we need to look for. Okay, produce some industrial sampling. I think mainly for the Leti, where they run different kind of batches. Okay, with where they are interested to have the stability of the process, not only 1 centimeter square, but many, and build a partnership with Europe, with France, of course, actors, but also with Europe. Okay, thus this is the ROSI 2, the status. Thus it's under our construction hall now. And here, the round here is, of course, we have a central robot to distribute the wafer either from one to one machine or to the other, or in both of the chamber. Okay, thus this is the reproducibility after 10,000 cycles. Thus now I thank you very much for your attention. Okay, thus oxide, the functional oxide on silicon. I think that this is the way to make the bridge between TRL3 and TRL6. because all the CMOS infrastructure are already there and so on, and the people know what is silicon. Thus, the aim of Phoebe is to produce a source of materials or make your material or your idea available and demonstrate on industrial tools, okay? And of course, my goal is to develop an industrial machine. Okay, that's how you can help me. Okay, but use my wafers, work with me. That's it. Thank you.
Thank you very much for this very inspiring presentation. So it's my pleasure to introduce now Christine Welsh from Vinci Technology and Vacuum Division. And so the floor is yours.
So good afternoon, everybody. I'd like to thank the organizers for this opportunity. It's very nice to be here and to be able to exchange with so many different people this afternoon. So I'm going to explain a little bit about Vinci Technologies, in particular the vacuum division. So you guys probably know quite a lot about us, but I'll give a recap in any case. We're located near Nanterre, in Nanterre near Paris, and we were founded in 1968, so over 55 years ago. And Vinci Technologies manufactures laboratory small-scale production equipment, and it's about 30 million euros with over 100 employees globally. Interestingly enough, we have our manufacturing in Paris, but we also have a manufacturing in Pune, in India, where we do actually some of the vacuum manufacturing also, which I will show you. To give you an overview, it consists of 4 different business units. 3 of those business units are linked to high-pressure processes, manufacturing equipment, like I said, at a laboratory scale for catalysts, rock and fluids, and subsurface analysis. And the 4th division, which is the division that I manage, that's the vacuum technology, vacuum nanotechnology division. So Vinci actually bought Michez 2000 in 2008. And I think here a lot of people will know Michez 2000 because they were created in the 1980s and they have over 500 systems installed, including a lot of the component business. And I think nearly every lab, at least in France, has Michez 2000 components, which is something that we're very, very proud of. And funnily enough, no matter where you travel in the world, you can. It's a bit like an Irish pub. You can find them everywhere. You can find Michez components everywhere. So it's the trademark of their green parts that allows us to identify them. I would like to draw a parallel. I've been working for Vinci for over 15 years. I'm very passionate about what we do, and I'm very passionate about the team that I work with, and with the people that we work with. I would say that we're extremely invested in learning constantly from what we do, and thanks to this heritage rich from Michez 2000, we have a very strong team in terms of precision engineering. So what we do is we tend to talk a lot. And I'm the right person for that job because I talk a lot. And we listen a lot to what the researchers and the industrial partners have to tell us with regards to the bottlenecks and difficulties that they're encountering during the development of their processes. So we're not necessarily trying to sell them quantity, but more so innovate and create new products and quality and equipment with them. It's not an easy task, but it's extremely rewarding and extremely interesting. And this is why we really rely on customer partnerships and we learn a lot from what we do. Now, reliability is an extremely important feature. So of course, we are using components and that you all know quite well. So we integrate from the component side of the business, VAT and Edwards and Amphichon and all the products that you've all been working with for quite a number of years. Our addition to that is basically coupling the chamber design and the mechanics of sample manipulation, sample handling around those reliable, proven components and products that are commercially available to provide you with the environment that you need in order to do your research. I believe extremely strongly in the integration of several different equipment on one unique platform. I've been observing the main and strong points of our business unit for the past number of years. We are known for making systems known as the mouton à cinq pattes. It's something that have that agility to be able to engineer these solutions. It's like practicing sport. The more you do it, the better you get at it. By integrating these different components into one platform, such as sputtering systems and MBE systems and UHV transfer systems, we are trying to facilitate some of the discussions we talked about this morning. That's accelerating science by collaboration, by training and cross-training different expertise and sharing to some extent those level of expertise so that we can learn and improve on these systems. So what we want to do is to be able to be a European full-scale UHV systems integrator, because we feel that we have something to bring to the table with regards to other solutions that exist today. How we do it is, like I said, we have a skilled team and we listen a lot to our customers, but I would say maybe a little difference is that we are very open-minded to collaboration, whether it be with what we have in our catalog or whether it be what's missing from our catalog or what the actual end user wants to do. So in that sense, we've worked with multiple projects all over the world, whether it has been here in France, in Institut Jean Lamour, but likewise in New York or in Israel, where we have done integration of several different systems under one platform. So it can go from MBE systems and sputtering systems to XPS systems, STM systems, ICP, RIE. Again, the objective is to be able to provide a platform for users to grow their materials and to experiment with their materials by making a solution that is adjustable and that you can grow with time. And that engineering, like I said, heritage, it takes time to acquire, but it's very important because we know how difficult it is for you to find funding, and we want to be able to be there in terms, in long term. In terms of applications, we target 3 segments, mostly. There's the renewable energy sector, where we do a lot of systems for perovskites. So these can be standalone equipment, or it can be cluster systems. We have a large cluster system in our lab at the moment, consisting of 4 perovskite growth chambers and a dual cluster chamber for transferring 100 by 100 millimeter samples. We also do 210 by 210, where we have growing, again, using our strong points, which I would love to invite any of you who want to come to the lab and check out these systems, where I prefer explaining in front of the systems themselves, but where we use masking systems to grow different layers and create complex structure for the perovskite industry and for the next generation battery industry. I also work in aerospace applications, where we do very, very large chambers for ion thruster systems or for liquefied natural gas systems. So This is also the second sector that we dedicate a lot of our engineering and time to. And the third system, which we're going to go in a little bit more in depth to, which is the quantum segment, where we do a combination of different platforms, as we're talking about earlier on. The idea is to do scalable solutions. I won't go into this very much in depth, but it is to draw the link between the projects that are existing that we've talked about earlier on today, and what kind of systems you can combine in order to achieve this. So by using sputtering systems for sub-angstrom layer growth, and very importantly for using ultra-high vacuum systems for the growth of multi-target and co-deposition. For this purpose, we have systems with up to 8 magnetrons, so you don't have to break vacuum and change your materials. Of the main research teams, we have the combined MBE and E-beam systems for the growth of different metals, and also for the growth of chalcogenides in the spintronic domain. We have our hybrid systems, as we talked about earlier on, which can combine organic growth and oxides and oxide preparation. And of course, the whole purpose of this is keeping everything under a UHV environment, because other than rising above 10 to the minus 6 millibar, as you all know here, can contaminate the surface, so we need to recover vacuum quite quickly. With regards to this, as you know, we have the large 70-meter tunnel that's in Institut Jean Lamour, upon which we have several different equipments, over 24 systems or small systems attached to it, including the molecular beam epitaxy, E-beam sputtering systems. But this kind of, we've grown a lot actually in the past number of years by through these transfer systems. We now also integrate cluster systems, which you can see in the bottom left-hand corner. It allows us to incorporate XPS and SDM systems quite easily onto the configuration. And here, we're talking about addressing the 2D material market. We work with a lot smaller samples. We're talking about flag-style pieces, but that can be combined on multi-block support or on simple wafer support in order to go up to 4-inch. So basically, the systems are constructed with heaters and sample handling that allow you to do simultaneously the flag-style support, also to do 2-inch, 3-inch, 4-inch. But again, that's a flexibility of having these multiple platforms working together. I think there's an important role of using sputtering systems for the non-critical layers in the growth of certain of these power devices and 2D structures, heterostructures, because using sputtering to do epitaxial growth means that there are certain design features that we incorporate from the beginning, such as being able to grow atom by atom over a very long period of time, several hours, means that you have to maintain vacuum pressure extremely stable. So using different design features such as double-walled cooling, or limiting through shielding the variations on your pressure, such that you can ignite the plasma at around 30, 40, 50 watts and then reduce in terms of pressure and in terms of power in order to maintain the plasma for long periods of time is quite challenging. And the influences during the growth of different heating and parasitic plasma that can happen within the chamber requires a lot of interaction actually with our end users. I think this is something that we talked about earlier on at the lunchtime break, is that we can't design this kind of technology just off a set of data that's published in a tender. You need to understand exactly what the researcher needs to do, what is the critical temperature that they will grow certain materials with, what analysis techniques need to be integrated in real time with regards to certain critical interfaces. For example, in terms of sputtering, when you're doing epitaxial sputtering, it is interesting to see how to integrate read into the actual PVD system. That is not something that is easy to do, obviously because of the magnetic field. And then in addition to that, if you want to play with the magnetic field of your magnetrons in order to be able to grow cobalt or cobalt iron interfaces, you also have to play a little bit with the balanced unbalanced effect of your magnetrons. So if you take that entire complexity and you try to put it in one system, it is doable. But it's very important then for us to be able to talk and understand with the users exactly where they want to go with their equipment so that we can provide them with the vehicle, so to speak, in order to get there. Because otherwise we miss the point, the system won't work, and everybody is frustrated at the end of the day. So like I said, in these heterostructure systems, you're talking about combining several UHV magnetrons into the same system. It's very important to have fast shuttering, which can be done through pneumatic shutters with encoders, and because once you have stabilized eventually the plasma at these low power, low pressures, you need to be open and closing the shutters quite quickly to do AB structures. So combining these sputtering systems in the UHV environment with MBE platforms on such a scale is critical, I think, for common projects to be able to advance towards what we talked about, like I said this morning, because things are moving quite quickly. So the more availability that you have to equipment by using transfer tunnels and cluster systems or vacuum transfer suitcases, the easier that you're going to be able to get a feedback from the different growth parameters that you have used. And that feedback is also helpful for us because then we know where we're going with the next component or with the next system. So for example, with regards to the MBE platforms, we do a lot of work on, let's say, high temperature substrate holders, so being able to go to 1200 or 1450 degrees, which mechanically speaking is not a simple solution. But it's something that we achieve by learning a lot from how long our customers are going to stay at those critical temperatures. And then in terms of the growth interfaces for these 2D materials, likewise, you see that the design of the equipment with regards to the sensors that you place in your system, we obviously simulate the fluxes from each of the effusion cells and from the E-beam, but despite that you have a certain amount of shadow effect on your detectors, on your sensors. That means that the positioning can become quite critical. As tungsten, for example, on the E-beam, placing the quartz sensor too close to the actual E-beam source means that you kill your quartz sensor immediately. However, rotating it on a rotatable flange can be a way to get around the problem. The selenium flux as well, using different, let's say, tricks by putting in cold traps or by putting in different types of shielding that can be removable, allows the MBE system to not be subjected to relatively frequent maintenance because these are quite volatile materials that we work with. And for certain of these 2D calcigenide materials, not necessarily going with a liquid nitrogen cooling. It's not always necessary, and it is an expensive overhead for laboratories. So again, not staying with the traditional methods, but listening and trying to understand what we can do to be a little bit more flexible. And then it's up to us to take the risk, because that's also part of the game. We have to be risk takers in this. We have to try to think outside the box and try something. However, I would say that what's very, very important for us as well is to be able to rely on systems that exist. And so we know our strategy of where we're strong, and we know exactly what type of systems we need to produce, and where we have a certain value to assist the research community and the industrial community. But we also have an operations strategy where we try to stay with a 70-30 rule. That 70% of the equipment, for the most part, should be something that has a certain amount of repetition. So the chamber designs and the pumping systems and the positioning of the different feedback sensors will be quite constant. But what might be a little bit different, and that's the flexibility, is we know the difficulties that you have in order to fit a chamber into a certain position, because this is the only position available. Or we know as well the difficulties that you may have in terms of sample manipulation. So what we do is we provide experimental data based on that 70% repeatability, and we work to strive on the 30% engineering so that you have a machine that's operational within a certain amount of time. For that, we use simulation data to match with our different experimental data. I won't stay much longer. I'll go very fast. But I just want to say that that's very important. In order to become an industrial solution with an R&D approach, you must be able to have industry readiness. And this industry readiness means that we really know the equipment that we're going to integrate into it, and we do certification and controls in order to achieve this. I would conclude by saying that thanks to the different partners that we have, for example, Institut Jean Lamour, CINaM, SpinTech, as part of this project, this is what has allowed us to grow and learn so much, and it has been a very interesting learning curve over the past 15 years. And I would say that for the future horizons, we talked about taking on students this morning. I'm very, very enthusiastic always about taking on students, especially M1, M2. I have lots of different projects for them. We have a lot of development in squid applications, on cryogenic film growth, on learning how to optimize the magnetic field, read integration, as I said, because we should develop this sovereignty here in France so that it is a soft technology that we can sell outside. Thank you very much, and like I said,
Thank you very much, Christine. So our next speaker is Jérémy Sylvain from Tescan, and so the floor is yours, and you have 15 minutes.
Yes. Hi, everyone. So nice to meet you. So today I will, in 15 minutes, talk about what Tescan can offer as a solution for nanomachining and implantation. And during my presentation, I will briefly introduce Tescan, because I'm not sure that you know well this company, not like my colleague before. And then I will go more in detail about UHV solution we develop called Nanospace, what it's really specific on this solution, and how I can imagine building interaction with the spin community. Okay, so Tescan, we are a unique solution provider to provide insight across all length scales. First of all, for your information, it's a really global technology company. The headquarters is in Czech Republic, and the company was established for Tescan in 1991. Orsay Physics, the French part, was in 1989 as a spin-off of Orsay University. And the company, we have many R&D facilities worldwide. We have some of in Brno, in Czech Republic, in the US, in Belgium, and also in France, in the south of France, where I'm based actually. In terms of technology, as I mentioned, it's a really large scale of technology. We are going from the STM FIB system to the 4D STEM. We have the UHV system. I will talk later about it, but we have also the micro-CT solution. We have now also some laser solution and also lift-out solution ex-situ. As I said, we have one of our R&D and production based in France. We are based actually south of France, close to Marseille, really, really beautiful place. You can see here some image. So we are close to Aix-en-Provence. It's really, really nice. So on this site, we have, as I mentioned, we have the production site, we have the R&D site, and we are making all the development, let's say, for the new generation of products that we can provide for the community, especially the nanospace that we have here. So what is the nanospace? So briefly, if you are looking at the history of the RC Physics company, at the beginning we were OEM supplier, meaning that, for example, during many years we supply different UHV column to some different manufacturers. For example, Schlumberger was one of our first customer, but during the year we continue to sell many different columns to different suppliers. But during the development of this product, we noticed that unfortunately sometimes, due to the fact that we couldn't control all the environment, let's say for example the chamber, the vibration, the active suspension, for example, or all these different parts, sometimes we couldn't reach the resolution that we can have on site on the company. So that's why we decided to develop our own instrument. Actually, I would say that it's really connected to what Lisa said. The idea was really to provide to the community an analytical FIB-SEM UHV solution. Because we can see clearly for this instrument, I will say 3 different applications that we can imagine and that maybe can be interesting for you. The first one will be the sample preparation in UHV. In this case, you will have the capability to prepare, for example, a UHV TM lamella or cryo TM lamella, or even prepare some atom probe tip thanks to this device. Then, for example, using a UHV transfer suitcase or a direct connection, we can go, for example, on different type of other type of microscope. For example, some STEM detector or TM detector, for example, the one from Nyon, or also we can integrate this UHV suitcase into the 3D atom probe for Cameca to perform some tomographic analysis. The second main application we can imagine, which can be really interesting also for the community, it's the UHV patterning or also the UHV implantation, let's say the nanomachining. So, and with this approach, you can really imagine to have some, let's say, workflow going from MBE systems. So many years ago, we worked with Reber to integrate our both solutions together. But also we can imagine to have a direct connection with some synchrotron line station, or also this large scale UHV interconnected facility that Christine mentioned just before. Finally, the last, let's say, main application that we can find with this type of tool will be related to the analysis in UHV. And also this is also really important, where actually you can integrate inside this tool different type of detectors. For example, some TOF SIMs, so to have some analytical information. You can also integrate some Auger detector, or also some AFM measurements capability. So typically, this platform is designed to work in UHV. As we mentioned before, this is really important to be in a contamination-free environment. This can be done because we have this capability to heat everything up to 120 degrees to perform some baking, but also we are paying attention about all the materials that we are using, exactly like we mentioned before. We are using the same supplier, of course, for our system to, at the end, to have this contamination-free analysis environment. So what is really unique in the nanospace system, I will say, it's due to the fact that it's a really versatile solution. Meaning that actually right now, my customers are not industrial company. We are working more for academic researchers. Meaning that all the nanospace are unique. They are really dependent according to the configuration, the application of the users. Meaning that according to the application, the customer will have the capability to, let's say, play a little bit with the configuration, play according to the type of the chamber, the number of FIB that they want to have, 1, 2, 3, the number, the type of SEM, the type of detection that we can add, or also the different third parties that we can imagine. The first part, which is really important, is the chamber. So this is a UHV chamber, but also, as you can see here, we have developed a 6-axis stage, allowing us to move, for example, here the wafer, to be in front all the different FIB columns. So you see, now we have the large rotation, moving the wafer to be in front the second FIB column. So like that, we can really have the best, let's say, specification for all the different columns. So I mentioned about FIB, because this is really important. At the beginning of the physics, we were the first company who actually develop and integrate a FIB column and install on industrial microscope. It was in 1991. At this time, it was for IBM, meaning that since more than 30 years, we are making FIB columns. So this is really our core components. And since all these years, we developed, let's say, a large range of FIB column. I will say the first type of FIB column that we have, more standard, will be the gallium FIB column. This is what you can find in all the standard system. We develop also the latest generation with higher current and better specification. But the second type of FIB column we develop, and also were the first one to integrate in a commercial system, was the plasma FIB column, where we can play with different type of gases, especially xenon first, but also argon or also oxygen. And 2 years ago, we developed a new microscope dedicated for the ion implantation, and to fulfill this product, we developed 2 new FIB columns. The one that you can have here on this slide. The first one is called Velos. This Velos is based on some alloy source, meaning that with this type of source you can implant, for example, gold, germanium, silicon, for example. And the second type is a plasma FIB column, where on this one you will have the capability to, for example, use different type of species, nitrogen, argon, oxygen, xenon, helium. Recently we have some user who did some carbon implantation, and this is really important. This is how we are working. We are always in connection with you, meaning that sometimes users are coming to me and saying, okay, Jeremy, I will be really interested to perform some helium implantation. So actually we did the test, we killed 1 or 2 columns to succeed to perform this implantation. But at the end, we find the good recipe, let's say, and now this is something we can offer to all the community. So, so this is just a few specifications, but the second main component that you can select for the platform is the SEM. This is electron beam column. We have 2 types of electron beam column. We have one which is a fully electrostatic SEM column. This is one that we have, for example, in Citizen. This one, it's really interesting because it's fully electrostatic, meaning that there is no magnetic field. So if you are integrating some different type of detector, kind of OG, with the OG detector, you can be sensitive to the magnetic field, and you don't want to induce this kind of artifact in your analysis. So that's why we developed this type of SEM. The second type of SEM that we are integrating, it's Brightbeam SEM that we developed in Brno, in Czech Republic, and this is electromagnetic SEM column. And so this is a bigger SEM column, allowing to obtain, let's say, the best resolution. So like that, you will have a really nice image where, as you can see, we can have a 1.5 nanometers resolution. So you can really observe small features in your sample. The last development we did recently was a development related to specific type of detector. I already mentioned it. It's called a SIMS, a TOF SIMS, time of flight SIMS. And we developed this technology to help the users, for example, to identify elements from, let's say, hydrogen, deuterium, etc., to molecules. And with this type of detectors, so first, if you compare with some classic standard analytical tool like EDS, as I mentioned, you can go from hydrogen, so you can really observe light elements, but we will have also a better sensitivity. We are on ppm resolution, so this can be also really interesting for some of your application. Something also may be interesting for you. We develop also a gas injection system allowing to the customer to perform some different type of deposition, to perform different type of application again. So, for example, you can use some cobalt, for example, to perform some magnetic nanostructure. This nanostructure can be done by both FIB or SEM according to your need, but you can also use, for example, the tungsten. But we are also working on new type of precursors. So again, according to your demand, your application, don't hesitate to tell me, and we will be really happy to develop new precursors. Finally, in this system, we are also working with other type manufacturer. So we are integrating some third parts. So typically for the suitcase transfer from, for example, for the MB to the nanospace or to the other type of UHV system, we are using, for example, the Verovac transfer suitcase. But also for some application, we are using the EDS and EBSD from Oxford. For the nanomanipulator extraction, we are using Kleindick. So, but we are integrating many different suppliers, so we are always open to answer to some specific demand. Meaning that at the end, this is what I said, we have one nanospace, one platform, but infinite configuration. So you can imagine to have a platform, let's say in HV. So in this case, this is what you can see here. There is no load lock, no air lock, and you are just opening the door to put your sample inside. So you are in HV, so you have not a really good vacuum, let's say for UHV people. We are reaching 10-7 millibar. But then, for example, you can have the same tool, but with the load lock and the air lock, and below not a turbo pump, but ion pump, meaning that at the end, you can have an ultra high vacuum environment. So in this case, you are reaching 10-10 millibar. And then on this one, you can also imagine to have the cryo capability, meaning that in this case, you can really perform your application in cryogenic condition at minus 160 degrees Celsius, for example. So, to conclude, which kind of interaction we can imagine with the spin community? As I said, so FIB is a really good tool to remove materials, but also ions are implanted. And we already mentioned that it can be a really interesting advantage for many applications. We launched 2 years ago this tool here. It's called Queen. This system, it's a dedicated system that we developed for the ion implantation capability. So for example, inside we're integrating a heating stage, allowing us to perform some in situ annealing. So meaning that like that, you can implant your ion and heat directly your sample up to, for example, 800 degrees to perform the in situ annealing. But not only, because we did some, we published recently with Alexandre Thaler from Chimie Paris Tech an article showing the fact that, for example, if you are performing the implantation at high temperature, at 800 degrees, you are improving your creation yield of vacancy by a factor of 4, for example. So there is a lot of interest for the ion implantation, but I will say that at the end we are always looking for some new development. Right now, for example, in astrophysics, we have 4 different PhD students working on 4 different applications and innovation. So I will say that at the end we are always looking for new partners to collaborate on the development, for example, of new sources. For example, we have some ideas that maybe it can be really interesting. So if you are by chance interested to for your application to work with some specific element or some specific application, don't hesitate to contact me, and I will be really happy to discuss with you. Thanks a lot.
Thank you very much. So the last speaker, but at least Stefano Bonetti for RARA Factory.
Thank you, Stéphane. Thank you, Vincent, the organizers, for inviting me here. So, RARA Factory, I go back to not to the already established company. We are a spin-off of the University in Venice. This is a startup we founded about, let's say, 1.5 years ago. But now we recently closed an investment round and we started to work on materials, really broadly speaking. And so this is something that I had to explain a lot to investors. So why materials are important. And the word of rare earth was something that, was, okay, yes, the professor of physics coming here explaining, the periodic table. Now, I don't know if thanks or because of some of the geopolitical tensions of some governments, we know this, unfortunately, very well. So a lot of the technology that we have depends strongly on these materials, rare earth. Well, we know this very well. People tend to confuse rare earth with critical raw materials. But the thing is that strategically, they are in the hands of one actor. In some case, the 99% of the production is in the hands of China. And the issues that with technology is what we know. So there is also a huge environmental issue with extracting them. I learned this by doing this adventure. The way that rare earths are extracted is extremely polluting for the soil. I know China is moving some destruction in Myanmar now because it's so bad. So we really, I think everyone, China included, if there is a solution to go away from rare earth, they would actually like to follow. And so what is that we did? So this is a founder that is myself and the former president of the University in Venice. He's a computer scientist. And then we team up with a bunch of investors, which now are on board. So we also have the commercial side. But the operational team is the key. So we put material scientists and computer scientists together to try to use AI to guide the discovery of new materials. And this is the challenge because let me see, sorry, I think there's one slide missing, but it's okay. So I'll tell you in a moment. This is what we raised recently to actually build this activity. So the reason why the slide is missing, but it's coming, is the fact that a lot of the AI that is coming down now, we think that we write something on a chatbot and we'll get the answer. The problem with materials, and I'm preaching to the choir here, it doesn't work that way. Materials are way too complicated. You can't imagine, or at least at the moment, the data definitely where the artificial intelligence our favorite we like to interact with, doesn't have the knowledge. I mean, it has the textbook knowledge, if you want, has read the textbook physics, but is not able to tell you, okay, if you do assemble these and these elements, you will get this material with these properties. This is not what they can do. The idea of doing this, of course, is very old in the community. I think when I graduated, when I got my PhD in 2010, it was machine learning to discover new magnets was already there. The thing is that both the machine learning was, well, less developed, and also we didn't have the good data. While the machine learning has improved a lot, the data is still a problem. So what we did now, what we are doing, is that we raised the money to actually try to do the thing that a material scientist would do to get the data from experiments. So to get a lot of data from the real world and then put into a model, which doesn't need to be so complicated as the one that are now famous, because the parameters are way less. But then they can actually learn because it has a lot of data that is coming from the lab. And the goal that we have is to replace all critical materials in principle with clean compounds. So we start with the magnets. That's also why this is, I think, is relevant to this community. But the idea, so what we did is an algorithm is very agnostic. So the idea is try to learn, and I will tell you in a moment how, from the data, get into a form that AI can learn, and then give you a new material which has the same properties of the material replaced, but made of different elements. So we start with magnets, and this is the goal. I mean, some of you may be working on this topic, so this is maybe redundant, but this is the typical, the world of magnets, in the permanent magnets is very in two, basically. It's ferrites and neodymium ferroboron. So you have the price and the magnetic strength, and I can tell you this is basically the BH max product, so it's the mega Gauss per Ørsted. And on top, you have the neodymium iron boron, expensive, very good, very strong. And then at the bottom, you have the ferrite, not very strong, but very cheap. And then you have, like, they basically take more or less, a bit less than half of the market each. It's about 35 billion euro per year. And then you get these two exceptions. Alnico, I learned that they mostly use, I mean, for a lot of specific application, but the one that probably everyone knows is the guitars pickup. And then samarium cobalt, which are the ones used for high temperature application in space, I think in some critical application. But there is, well, there are a few issues. Of course, the thing is that samarium and neodymium are two rare earth. This is the things that we want to get rid of. There is also an interesting thing that I learned by doing this, that there is an empty space in between them. But this is, people call it, there is the possibility of doing gap magnets. And talking with industries, there is a lot of applications that do not require the neodymium magnets, but they would be very happy to have something which is better than a ferrite. So there is a lot of space. If you can find something that is even half as good, and but cheaper and doesn't particularly depend on rare earth. One of the companies we talked to, they had their working electric motors made of neodymium magnets. At some point, the neodymium magnet price went up a factor of 10. The motor was not commercial anymore. So, and they say we don't need that much. We could live less, but we know to make sure that the material always arrives. So this is the kind of thing. So there is a lot of opportunity. Well, of course, to try to find something even better than neodymium, but even if finding something between which is performs. One thing that's not put here that a lot of industry requires that these magnets work at 120 C. So they have to work in warm environments. So it doesn't have to be room temperature only. So what we do is that we patented a method which combines, well, material physics, network theory. One of the founders is one of the world experts in network theory, and then artificial intelligence. And basically what we created using network is a sort of a map of the material based on the properties. In an original way, in a sense that the way to make a material become a mathematical object, there are two things you can do. One that everyone is doing is the composition. You make the composition, it becomes a mathematical object, and then you put in your machine learning. The other thing is try to make it another object, a vector, let's talk to it, that has somehow embedded the properties, because that's what we need, how it works. So the way we did is to try to make a map. So we managed to make a map, and then what we are making the AI learn is trying to find connection between the composition and the properties. Okay, navigate into this map. But basically, what the loop is that we have the database that we're building, or you do the computation. You synthesize the material in high throughput. I will tell you how high throughput, what we mean, and then you characterize. So every material that we do, we make it, we characterize it, we send it back to the computer. Okay. And so this is where we arrived today. I think today we reached. I checked on the logs, 22,000 materials. So we're a bit above what I said here. I have to keep updated. So we set up a system that we make 100 new materials every day, we already bought a second. We're doing this by sputtering to go fast. We do rather thick films, to 200 a day, and then we characterize each of them. Of course, I mean, you say, so you want to do permanent magnets, you need to do bulk. Definitely it's true. So what we do is that, of course, this is the high throughput screening, and then we identify some interesting candidates. With that, that we now need to go outside, but the idea is that we need investment to do it in-house than to do the actual sample, the bulk, the material. For other applications that was discussed before, multi-layers, this step is not needed, so you could use our process in the same way, and then already have the film that is interest to you. And the interesting thing is that even before, so of course we did, well, one of the things that I discovered by doing all this thing is that the existing database of materials are really poor, especially of magnetic materials. And sometimes they may have some good data, but it's too spotty. So we really wanted to have like a nice clean table with the composition, measure properties, and we measure magnetic, electric, optical, thermal properties. Soon we're going to measure the mechanical properties. So we have a set of nicely measured properties and for all materials. This is now, the AI learns very well if you do this, and we have signs that this works. So we are building our own database for do the magnets. And this just to show you, this is similar to what was shown before. This is, we already, just by starting like this, we discover like about 20 families of new magnets. I tell you, I haven't found a new neodymium magnets, otherwise I probably would be in a very different condition with the company. But it's moving in the right direction. And you see here what is surprising. We found, of course, we reproduced, everything is known, we can reproduce. We found some interesting thing, and the fact is, I wouldn't say everything, but I would say we bought half of the periodic table in pure elements, and we combined in a different way. We do ternary, quaternary, quinquenary, some sexternary alloys. But there are regions in a composition. Here is, I would say, is probably 5% changes in one of the elements. You tune this a lot. If you are outside the specific range, you see like either, a bore is super soft, if it's iron magnet, or you don't see anything. So, but there is a range of composition where you really can see the coercivity go on. In the end, what you want to maximize is the area of this loop. Okay, so what is interesting also, this is something I learned by doing a company, you have to always to check the price. The things, that of course, we are using cheap materials, but we found extremely, extremely cheap magnets, way even cheaper than ferrites, and that they are available everywhere. The nice thing is that, of course, since you have access to many elements, you can tailor one composition for a specific country. You can imagine that you can actually, you have the resources there. The way that we make, well, we hope to make money, we're starting to do some, but not much yet, is to actually have royalty-based licensing or also some joint venture. The royalty-based means we patent the material, and then we sell the license either in an exclusive way or on a non-exclusive way. It could be also depending on the sector, and also to do joint venture with some of the producer. The big thing, of course, is also then to scale up the production. This is something that requires a completely different type of investment. But the need for this kind of material is so large. I mean, really, we didn't look for any companies. We get more requests to interaction than we can deal with at this stage. So I was asked to see what could be the collaboration with pepr-spin. Sorry, I know there are several programs. One thing that is, I think this community, since I did my PhD in this community, so I know very well, one thing that I think investors are starting to appreciate how complex materials are. Well, some of the investors told me, we really don't understand what you're doing, so we needed to trust you. But they really start to get that materials are a complicated thing. And I think this community has, well, a tool of expertise and tools that are really expensive. And it's very hard for a startup. I mean, I cannot imagine to buy every tools I need. I mean, in some cases, we need a synchrotron. I cannot, with a startup, decide to ask money to build a synchrotron. So the fact that there is a community that is attentive to these things, that can provide access to your facilities in a way that is fair for everyone. We did a deal with the University of Ca' Foscari, which the University of Venice, where of course, I'm still a professor there, so there is an IP related to that. But there's a fair, we file together, then we get the IP, but the university gets a royalty if things goes well. So there is a way of engagement that can be advantageous to both. So I said my company, RARA, but it could be for any company. There is one thing that, we pay for the development of a new part, because typically what is needed to do this kind of exploration is the high throughput capabilities. So you need some sort of robot, you need some sort of software to control. It's to go fast. one could do it together and then we share everything, or we could take care of it, and this could be that then you can still use the thing, but of course the AP needs to go back to the company. This is one of the things that is also, there are a couple of French startups that do something what we're doing. There are a couple in Germany, similar size as us. Then you go to UK, US, you have 10x the size. But this is crucial if these things has to work and bring a lot of attention and resource to the community, that somehow the AP needs to stay in the company, because the investor, at some point they want to sell the share of the company. So it needs to be easy the way that this works. That's the only thing that I would tell to this audience, that this was new to me when I learned this. But this, I would say, is the thing that could work. So use the fantastic facility that this set of labs have to actually do collaboration, and and then find a fair deal with a potential startup like us. I think that's everything I wanted to say. Thank you.
Thank you very much. So thank you, Stefanos. Thank you for all speakers. So I think we have a little bit of time for this roundtable. So if in the audience you have questions to one of specific speaker or to all of them, this is a good time to do. Manuel.
I have a question for Stefano. This is Manuel Bibes. Nice to meet you. So basically you're doing cost sputtering. Do I understand correctly that you are doing cost sputtering?
Yeah.
So you use like 3-4 different targets, and
we can do up to 7. Yes.
Up to 7 at the same time.
Yeah.
And then you have a big wafer. You rotate.
Well, I don't tell too much. I think. So it may be better to use, instead of doing the gradients, we sought for uniformity to mask. So we do a lot of, we mask, and it's that expensive part to automatize the mask, to actually get, so you get a wafer, you get dots of alloys.
Okay. And the characterization you do is like you do X-ray and magnetometry?
We do more. We do magnetometry, we do transport in a fast way, we do optical properties, we do thermal properties, and on the interesting one, then we do the X-ray and we do all the annealing process. So we only do room temperature deposition to go fast. Then when we have a proxy that something is interesting, then we dig down, we do X-rays, we do everything on that. Yes.
But you have a DFT step before that to
Nope.
Just do like okay, right.
We're thinking of adding that once we found something, because it's very hard if you do this. I mean, we really have 50 elements that we can mount. It's really hard to tell someone DFT with no prior, so tell me if this is interesting. So now we're thinking, and we have a collaboration, we're setting up a collaboration with Nicola Marzari in Cambridge. If we find you an alloy that seems to be interesting, can you do the DFT explains why is that, and can you maybe suggest what doping we need to do? So we're doing the coarse exploration, then we try to do the fine. I think in some way you need to find a compromise. I'm not sure this is the best way. We think it is the best, but there could be other ways. But you need to have a lot of data and then do the fining when you find something interesting.
Okay. Thank you.
All right. Any other questions?
So thank you for your talk. I think the idea that you presented in RARA is very promising. I just have a question, more like a curiosity. Do you take into account in your process somehow the microstructural defects or characteristics of your films, and how could we optimize this into a machine learning process?
You touch a crucial point. So in the fast scanning, no, but once there is something interesting, we go and look what happened, because typically when you do have the cursivity, there is also something related to it. So we do then all the microscopy analysis and everything. So we are thinking of doing it. The problem with the AI is the amount of data. So we would need, and this is maybe something we could do, that we need a fast screening. I don't know what is the fast way to see the microstructure of all the sample. If we have that, we know how to put it in. Is that we don't have enough data. That's always the problem. But if there is a way to do this, I think it would be super interesting, because this is the thing that we had to sacrifice. We know it's important, but we do it only on the interesting one that we found. But it's spot on. Yeah.
Okay, thank you. And are you planning to do this on oxides?
Yes, but the problem is that I would need other I don't know 10 millions or something to build the thing, and the oxides are much more difficult to grow. I'm not an expert. I mean, I know a little bit, but I never grown. We started with metals to prove the idea. If that works, I think the investors and the community, so they will have more passion and they believe that it works. And then, they give you more money to buy more expensive equipment to do the stuff. But I would say the safest bet is to go metals because they mostly mix. I think if you go oxide and don't know what to do, probably you get not good quality. The metals we get are pretty good. Yeah.
Okay, thank you.
I had a question on the side of Tescan. Sorry, it's a focused one. I was curious about the Eclipse equipment that you mentioned with electrostatic lenses. I think we have been many to see magnetic contrast in SEM, especially when you have magnetic materials like permanent magnets, which have a strong magnetization. I hear from colleagues that the development of magnetic imaging is SEM is under development, sometimes in reflection, sometimes also in transmission, which requests some specific detectors behind. Is it something that you have heard of or in mind or not at all?
In terms of detection?
Yeah, magnetic imaging with SEM, which can provide nice resolution and much cheaper and more versatile, for example, environment that you would have in a TEM.
It's a good question. So I'm not aware. We are working on different type of detection. For example, recently we show some, due to the fact that I mentioned before, we are doing some implantation. We are working at really low current, so we are something like 100 femto. So we develop a new way to detect, for example, using the current itself, the stage. So this is a way we are doing, for example, some imaging. But for the magnetic approach, I'm not familiar, but I can discuss with my detection team, and it can be interesting.
Okay, thank you. Any other questions, especially on UHV equipment builder?
Frédéric Petrov, CNRS. Yeah, maybe a question for Vinci and Ribert. How do you expect AI to impact your machines in terms of control of the machines, software of the machines? Do you expect that you already implement something, or?
I will first answer for Ribert, and after, yes, so we are implementing AI for our machine. However, this is the quality of the data. The data is the key to implement AI, okay? Thus, this is also the reason why, especially for oxide grow, where the process for the grow is very tiny windows. This is also the reason why we operate the machine by ourselves, so has that to implement the proper AI to improve the tools. But yes, already on standard machines we have AI.
And I would echo the sentiment that the data is the most important feature. Again, we're a bit lucky to have access to platforms such as Institut Jean Lamour, where we can grow some equipment, grow some layers, and then get some analysis. But in addition to that, I think that it's a lot to do with the simulation data that we use as well, because I think it's important to use that predictive scope in order to do the machine learning eventually with the data that we have and to know where we're going. So one of the things that we are working on at the moment is target usage with regards to the magnetrons, being able to decide when you need to change your targets eventually. So it's small steps towards building and using the data with regards to simulation, so that it becomes easier for the people in the future.
Any other questions? Yeah, Frédéric again.
Yeah, maybe to Stefano. I think the most important market for rare earths or related magnets are they are bulk magnets. So how, to which extent your results could extend to new bulk magnets?
Yeah, no, it's, I mentioned it quickly. So we're going rather thick films, and ideally, yes, we need to check it works. So we have a partnership now with a research center where actually, I think in 2 weeks, we start to synthesize the first. So we start from powders and we try to reproduce. We believe that, I mean, there are methods like that are most likely, I mean, demonstrated that they can reproduce you know, if you have something in thin films, you can reproduce it. The big step, so I'm not worried about the actually that we do the prototypes. The thing, if it's compatible in an industrial process that actually is more or less already existing. So the good news, I learned also this, is that the actual rare earths are particularly hard to melt. So if you do something without rare earth or with less, it's actually, it could be simpler. But you're right, it's a point, so we are not exploiting, I mean, of course, if I will start to do multi-layers, good luck with making a bulk. We're really doing alloying the simplest as possible. We try not to do anything with the films that, you know, is a trick to show that we have something that we cannot reproduce. So we will see it, but, you know, it's always in our mind, and we will soon be testing the first ones. But yeah, it's a good point.
Thank you. Any other questions? Yeah.
Maybe just to conclude, maybe on each of you, if you can think on one single item that you saw from the PPR day that you think the community can help you to improve your products, or how to collaborate with. One single thing that you think will be a, I mean, main improvement in your products, or type of collaboration that you could have with the community, just to make it more practical. The order you want.
For our case, of course, is simple. Work with me to build new materials on silicon and let make this new device having an industrial life.
So you mentioned this BTO?
BTO or other, because these platforms, okay. You are the architect, you know the material, you know the interface and so on, okay? Because we are a system maker. Okay. Of course, making this on small scale, it's fine, it's perfect, and so on, this is TRL3, but at the end, if we want to interest industrial and make it goes more further, we need to have at least a demonstration on large surface.
Okay. She's from the community.
Yeah, okay. Well, okay. Maybe you found something in the community.
The only thing that what maybe we could do at PAPR to facilitate communication, because a part of the community is here, but some people are not there. So maybe that's something we had to think about what we could do, so we can discuss in a most easy way.
Yeah, just to complete in that sense, I mentioned this morning that this is in SpinMat project, so this transverse project on material characterization. One task we have for this year, we want to do kind of a standardized description of the equipment that will be accessible, easily accessible, and shared with academic community, but also with industrials. And we are, I think, willing to collaborate and work together, having some specific conditions depending on the demand, of course. We like to work, but maybe not for free forever. But this is one of the objectives of this national infrastructure that we want to do this year.
Yeah, if I can answer, I was thinking exactly the same. So I have an easy overview of what, because you're a huge community with a lot of unique instruments that really are, I mean, sometimes there is one or two in Europe, maybe. It's difficult to get. So to get this access to know. So for example, I discovered by chance, in my university in Venice, they just bought an XRD, which had the automatic loading, which actually was wonderful. No one thought these kind of things. So knowing the equipment, thinking about deals already, like, paying the access to what I said, being kind of ready so that we don't waste time in, writing contracts, that we do a fair deal. It's good for everyone. And the other thing, if you're interested, because this is something that I learned is actually very fascinating, and is really getting a lot of money from the for industrial world, doing a thing in an automated way. So I learned, like, you know, a month ago that now the new cobots, the robotic arms, you can find something for a few €1,000. The coding now, you know, you do it with LLMs, so you really can get your lab to get to do these things. Could be interesting for you, but this could be useful to have, like, you know, less human, for the boring stuff, like moving sample, like doing a lot of scans. This is something that I think there is a lot of interest. You would find interest in people helping also develop this.
On my side, I will say that I will need your feedbacks about which kind of modification we can perform on the samples that we can prepare. I mean, if, for example, you are some idea saying that, okay, for the next generation, we will need to have a specific ion inside this typical sample, I will be really interested to know, because actually you are giving me this kind of feedbacks, and then I can say to my team, okay, let's see how we can make this type of implantation or modification inside the sample, which type of dose. For example, recently one of the customer asked me to make some really low current implantation, something like 0.7 femto. So you can imagine it's really low. So this is exactly what I need. I need to have this kind of feedbacks from you, because you are working on the next technology, on the next generation, and so you can give me some feedbacks about, okay, how will be the future, what we will need, and then like that I can challenge my team.
I think I would take a very pragmatic and practical response to it, is that I think that a lot of the time we don't know the existence of certain of these programs, and it's very important from us, from an industrial point of view, to be involved and to have this communication clearly, because unfortunately, especially for the smaller to medium-sized enterprises, especially in France, a lot of them are dying off. A lot of the let's say the artisans that have a wealth of knowledge in their head in terms of manufacturing these materials, they're not able to sustain and survive. So everything comes from say a top-down level. You have a certain problem to solve with regards to the research and with regards to the materials. AI is accelerating really rapidly. We can't forget that a lot of the knowledge is still in the heads of all these experts, and we need to preserve that, and we need a continuity, and we need to involve students, like we said before, and allow this transfer from person to person. I think it's important that we don't forget that in the light of how fast things are going these days.
All right. So with this, I think it's a perfect conclusion, and we can move to the coffee break. Thank you.